As we discussed in the last session, Einstein's theory of relativity supersedes Newtonian mechanics. But we understand that we don't always have to do every problem doing a relativistic approach. And so it's probably good to examine just in what ranges we do need to use relativity if we want to get a certain accuracy. So we learned that Newton's second law still holds, where the time rate of change of momentum is equal to the sum of all the forces. However, the definition of the momentum is not the classical definition of momentum, the mass times the velocity, but it has this other factor in it in the denominator, 1 minus the square root of 1 minus v over c quantity squared. So this factor, the Lorentz factor, is given a new name, it's given gamma, and so I'd like to explore this function and see how it depends on velocity and what it looks like in intermediate velocities. So the velocity of light is 3 times 10 to the 8th meters per second. It's quite fast. And in the limit where the ratio of v over c tends towards 0, the low velocity limit, gamma tends to 1. We simply say that this term is small in comparison to 1. This drops away. We have 1 over the square root of 1. We have gamma equals 1. So that's just the Newtonian definition. For small v over c ratios, we get gamma equals 1, and the definition of momentum returns to mv. So on the other extreme, however, where the velocity of a particle approaches the velocity of light, gamma diverges to infinity. The function gamma is not defined for values larger than the ratio v over c being 1. So as we approach from below, gamma diverges like this. All right? And whenever you have a new function, it's always the first thing you should do is graph it to see what its behavior is. So down here, gamma is approximately 1, the low velocity limit, Newtonian limit, and up here we have the relativistic limit, where gamma is diverging. We're primarily going to be concerned about this intermediate region today, where gamma is not quite equal to 1, but it hasn't yet diverged to very large values. So how are we going to approach this problem? Well, we're going to use a Taylor series expansion. Many students learn Taylor series expansions in their high school calculus class. However, it's quite typically the last thing you do. You do it sometime in May when everyone's thinking about graduating. And many students turn out to be not terribly comfortable or not terribly knowledgeable or just need a bunch of practice with Taylor series expansions. The general notion is I have some function, such as the gamma function, and I want to know approximately how it behaves around some point. So let's pick half the speed of light. So in this range, the value is not quite equal to 1, but it's not diverging to infinity. I want to know approximately how the function behaves around the value the speed of light equals, or half the velocity of the speed of light. How can we do that? So this is the prescription. It says that if I want to know how a function behaves around some point, so in the case that I gave you below, half the speed of light would be what x0 is, dx, delta x here, just says a range around that. This delta x is meant to be small in comparison to the value that I'm comparing, or it's supposed to be, in some sense, a small range. Then the first thing to say is I'm going to approximate the function by simply its value at the point at which I'm expanding around. So for velocities near half the speed of light, the function is going to be approximately equal to the function at half the speed of light. Sometimes that's good enough. If I want to do better, I want to find the slope, or the first derivative of the function, near the point of interest, and then multiply it by delta x, the amount that I vary from that point of interest. Okay? If I want to do better yet, it's 1/2 the second derivative. I give it some curvature, then times the best parabola is going to fit delta x squared. And there's a third order term which has the third derivative in cube, and this is a general expression, and it's an infinite series. 1 over n factorial, the nth derivative of the function evaluated at the point that we're interested around, times the delta, how far we are away from that point, to the power n. All right? And in the limit of an infinite series, this defines the whole function for large values of delta x. If, however, we want to just use small values of delta x, we notice that delta x squared is smaller than delta x cubed is smaller yet, and so these are ever decreasing terms. So for small regions of delta x, it might be perfectly reasonable to truncate this and only look at the first and second terms. And that's what we'll do in this discussion. So let's take a concrete example. So here is some arbitrary function. I haven't written down an analytic form for it. I just drew it out. And I want to know approximately what the value of that function is around x0. All right? So the red function is evaluated at x0 and gives me f of x0, this blue line. And so I might say that in some range, this red line is approximately equal to the blue line. Well, all right, so it's approximately. It doesn't look all that good, an approximation, but it's approximately so. If we want to do better, what the prescription says to do is to find the slope, that's the first derivative, evaluated at x0, and then multiply times delta x. And that's going to give me some change in this value that I'm going to have. And so that's what the green line is. So the green line adds in this next term of a linear line, right? The slope times how far I am away from my point. And so you can see that the difference between the red function, the exact function, and the green line in small regions is actually quite small. Now that we understand how pictorially, schematically, we can find an expansion and approximation of a function around a point, let's turn to a concrete example. So here let's examine the exponential function, all right? And we want to look around where x equals 3. So we're going to try and define values, how to approximate the exponential function around values near equal to 3. Well, our prescription says to do this, that the expansion, that the exponential function near x equals 3 is first equal to the exponential function at 3 plus the first derivative of the exponential function. Now here where the exponential function is special because each of its derivatives is the same as the original function. So this is the first derivative evaluated at the point we're concerned with, 3, times the difference, x minus the point we're concerned with, 3. Then we have 1/2 the second derivative, which is again the exponential function, evaluated at the point of interest, times the difference squared, plus a third term, 1/6 the third derivative, evaluated at 3, the difference, x minus 3 cubed. We can turn to look at the graphs of this function. The actual exponential function is shown in black, the dark line here, and we have the 0th order approximation, just the constant evaluated at exponential 3, shown here in orange. That plus the first order linear term is shown in green, the straight line. The second order term is parabolic in shape, and that's shown in red. And then the third order term is shown in blue, and the third order term agrees so well with the function, at least over this range of values, that we really can't distinguish between the two. We can look so close to the value 3, all of these functions are doing a pretty good approximation except for just the constant term. Right? However, as we get out farther, we see first the green, or the linear approximation, begins to fall away. If we move farther yet, we can tell the difference between the second order approximation. So the higher order terms in the approximation do better over a larger range. Now, this is over a scale that's quite coarse. All right, so we have this is a difference of 10 in the function. We may want to be more accurate than that. And so we can look at now a scale of the error just on the order of 1, or a 10 times higher factor. And here we can see that the constant approximation really does very poorly. It almost approximates the function nowhere on this scale except for the exact point x equals 3. The linear approximation, shown in green, has a smaller region of validity, so maybe if I were working just around 2.9 to 3.1, I could use my linear approximation. My quadratic approximation, shown in red, certainly has a range over which it does quite a good job on this scale. And my third order approximation, shown in blue here, is really hugging this line x equals this line of zero error for almost this entire region. So with ever increasing order of approximation, you gain a larger region over which the approximation is successfully approximated. We can do the same thing turning to a different function, the sine of x. And here I've expanded around x equals 1. And you can see again that the constant term doesn't do a very good job. And the linear term has a small range. The green line has a small range where you can't see any difference. You put the parabolic and the third order term in. These have larger ranges, but the important part here is none of them can actually do the sine function oscillating up and down over a very large region. It would take many, many terms being added to this to actually be able to get all of these oscillations in. But over a narrow range, this can be quite a good approximation. So why were we discussing this at all? We were discussing this because of our expression gamma. We wanted to know how to evaluate gamma near, say, half the speed of light. And we didn't want to use the full radical, but we wanted to find some sort of polynomial expansion for it. So we'll do our same Taylor series expansion now, but I'm going to look first at, not instead of half the speed of light, but let's look at low velocity expansion, where x is going to be around 0. So my velocity is close to 0, and delta x in this expansion is going to be v over c quantity squared. So this is my small quantity is going to be v over c squared. So then our function is a function of v over c quantity squared. And I could have put a 0 here for x0, but I chose not to write it here. So I have 1 over the root 1 minus delta x. So delta x is my difference from my velocity of 0. It's going to be my low velocity limit. This is our power series expansion, the Taylor series, and we're going to carry it out for 3 terms. So term by term, it says my first term is that when I have low velocities, I'm near the velocity 0, then I will just put f of 0. And so if we look at our expression, putting 0 in here, all right, we get f of 0 is equal to 1. So our simplest approximation is just a pure Newtonian value. Gamma is approximately 1. So this is good enough for lots and lots of things. But if we want to do better, we have the second term, which says take the slope, evaluate it at 0 velocity, and then multiply it by how far away you are from 0 velocity. So we need to take the derivative with respect to delta x of 1 over root 1 minus delta x. And all of you can take this derivative. And I've done it here. So we want to take the derivative of 1 over the root 1 minus delta x. And we get 1/2 1 over 1 minus delta x quantity to the 3/2 power. We want to evaluate this at delta equals 0, or actually this should be delta x equals 0. And so that is just putting 0 in here. We get the value inside the parentheses to 1. We get 1/2. So now it says that our next approximation for gamma is the Newtonian term 1 plus 1/2 delta x. Delta x is equal to v over c squared, and this is the first order approximation in v over c squared. So v over c is appearing as a square there. All right. If you carry it one term more, you can get the second order approximation, which is now v over c to the 4th power, and the coefficient out in front is 3/8. And so you have to take a derivative to do that. And you really should do that so you know how this proceeds. The general expression can be written down in a closed form here, where it's an infinite series, where n is giving us the powers of v over c to the 2n. So only even powers of v over c appear in the series, and that's what we saw up above. We had the 0 power, the 2nd, the 4th, the next one will be the 6th, and the 8th, etc. And this coefficient is given by this product, where the product runs from k equals 1 to whatever n is of 2k minus 1 over 2k, multiplied that sequence together. All right? So let's look at how well we do with our various approximations. So the Newtonian approximation is just the constant value gamma is equal to 1, and that's shown in red. And on this scale, it's pretty good for low velocities. You can't really tell the difference. When we add in the linear term, we get our orange line. And so you can see that bends up some. And then the linear term has a v over c squared, so it does have curvature to it. The next order term has a v over c to the fourth power, and that's the green. And so that deviates less to even higher velocities, v over c. We can look at the errors, as we did before. All right? And the black line here shows a 1% error. So up to what velocity can we tolerate a 1% error? Our first order expansion, just using the Newtonian expansion, shows that I can go up to almost 30% of the speed of light and tolerate and have a 1% or less error. 30% of the speed of light is a very rapid speed, very high speed. We're not going to be finding baseballs in cars at that speed. However, if I then take the next expansion, the v over c squared expansion, which is in orange, I can get up to 40%. I guess I said this was 30. I misread. This is about 15% of the speed of light. You can have the Newtonian mechanics. Up to approximately 40% of the speed of light, we can go with just the v over c term. And if we want to go higher with its next order term, we can go out to maybe 60% of the speed of light. Now, this was being able to tolerate a 1% error. 1% is actually fairly crude. If we go down and say I want to have 0.01% error, then we can see we can go out to a fraction of light which is maybe 0.015, all right, or a little less than 1% of the speed of light, and still have 100th of a percent error. And the second order expansion does better, and the third order expansion does better than that yet. So just depending on how accurately you need your result to be tells you how far you can live with the Newtonian value versus having to go to better approximations for the relativistic calculation. Now, there's one more thing that's very interesting that we can do with this. Quite possibly, the most famous equation in physics is Einstein's E equals mc squared. What's so revolutionary about this is it says that mass and energy are equivalent. They have a coefficient in between them, but I can change mass into energy, and I can change energy back into mass. So this is something that is just not a feature of classical mechanics, Newtonian mechanics at all. Now, in the 20 years ago, one used to say that the total energy of a body depended on its velocity in a way that allowed its mass to increase. And so we used to talk about a relativistic mass that increased by a factor gamma. So m sub 0 here is the rest mass. If I took a particle and I measured its inertial mass at rest, I would get m0. And if I then put it into motion and were able to measure its relativistic mass, it would be increased by a factor gamma. All right? Now, this type of nomenclature has fallen out of favor, and I'll go into that a little bit more. But let's use m0 as the rest mass, right? Then it says we have a rest energy equal to m0 times c squared. So this is our rest energy, just the energy a particle has by existing and having mass. The total energy in a classical approach would be my kinetic energy plus my rest energy. The total energy then is the relativistic mass, which is given by gamma m0 c squared. So we have our energy increasing as a function of velocity, and that has to be equal to my kinetic energy plus my rest energy. And so if I go ahead and solve for my kinetic energy is relativistically, my kinetic energy is equal to gamma minus 1 times m0 c squared. So this is now the relativistic expression for kinetic energy. That's not something that we're going to see out of Newtonian mechanics. But what if we look in the low velocity limit? Does this return to something that we have seen before? If we take the first order expansion, which is gamma is equal to 1, it says our kinetic energy is equal to 0. Putting gamma equals 1 into here. So, yes, if the velocity is very, very close to 0, the kinetic energy is very close to 0. But I'm afraid that doesn't tell us very much. So to do better, we'll use the next level expansion in gamma, which is 1/2 v over c quantity squared. So substituting this in for gamma, we have 1 plus 1/2 v over c squared minus 1 times the rest energy. And this, the ones cancel out, the c squareds cancel out, is equal to 1/2 mv squared. The kinetic energy equals 1/2 mv squared. That you probably are used to. So I think it's really a very, very reassuring result that we could start out with Einstein's energy mass equivalence expression and looking in the low velocity limit, expanding gamma, return to kinetic energy equals 1/2 mv squared. So this is nothing other than the first approximation to relativistic energy, giving us our kinetic energy 1/2 mv squared. So I think that's a very nice result.